FDP 5 talks have been completed very successfully, and or a kind of so being this topic is the only to area have got a little and I all of still reach understanding of this of polymer chemistry, but I would try to conceptualize the things at my level best. So let me start. The contents of the talk are, first of all, we'll discuss the storage, which is basically can't stay away from energy devices, and there is an ever increasing demand of such devices, but there is a crisis of such storage devices also, which is onset now, because the conventional non-renewable energy sources, which are mostly fossil fuel, coals, and etc., they are about to get depleted. Though few tens of years we'll be able to survive with that, but ultimately we cannot expect our long future to be dependent upon such devices. That's why such energy sources. That's why you might have seen that these days electric vehicles are in so much trend, and every month you see that the technology is growing so fast that we think that after some time, these electric vehicles, which are currently very expensive, we expect that with the advent of technology, this electric vehicle will come in a cost regime where it will be available to a common person also. So the solution to this energy crisis is absolutely renewable energy sources like solar and wind energies are unconditionally naturally available to all of us, so they can be used, and the stored energy can be utilized later as and when required. But what is the problem? The problem is that the nature doesn't provide us a control. That means there is no human control on the amount of the energy. Like there are various factors, temperatures, humidity, etc., which will govern the daily basis dosage we get for this energy. So the major challenge is to have some stable energy storage mechanisms for this renewable energy, for harnessing the energy from this renewable energy sources. So here I have shown you some potential energy storage devices. The first one is our capacitor, which is conventionally known to all of us. Then second one comes battery, then fuel cell, and at the last I have put supercapacitor. So out of these 4 energy storage devices, 3 of them I have encircled, because the first one, which is the capacitor, is a little bit different in terms of the charge storage mechanism. So because capacitor stores the energy electrostatically, so I have kept it separate, and the rest 3 of the devices, they store the electricity electrochemically. So we have kept them in one group. So except capacitor, all these 3 devices have following similarities. First of all the devices store energy electrochemically. Then all comprise of 2 electrodes in contact with an electrolyte. Then electron and ion transport are separated, and the energy providing process takes place at the very phase boundary of the electrode and electrolyte interface. So this 4 points are common in all of these devices. Now we see how this energy storage takes place. So as I have already told you that electrochemical mechanisms are utilized in these 3 devices. So these electrochemical energy storage mechanisms can be classified in terms of Faraday and non-Faraday. Faraday process is also known as direct method. That means the charge storage will take place via the redox reaction. Here you see that at the surface of the electrode, there is a transfer of electron between the 2 species. That means electrode and electrolyte ions. They have an exchange of electrons, so that charge storage takes place via this reduction oxidation reaction. And other one is the indirect method, where there is no chemical reaction or no exchange of electrons between the 2 kinds of ions, but simply this positive, say for example, if this is a positively charged electrode, then there is an electrostatic attraction for the negative ions. So this positive and negative charges come close together and they form a double layer. We call it a double layer because I have not shown you the inner Helmholtz and outer Helmholtz planes. Otherwise, a single monolayer of negatively charged ions will be there, and then solvated ions come after this inner Helmholtz layer. So that's why this is known as double layer. Now, I just start discussion with the capacitor, because supercapacitor is a kind of modification in the capacitor only. So we all know that when 2 metal plates are separated with some distance and a dielectric medium is inserted in between, then upon charging these plates, positive charge appears on one plate and negative charge appears on the other plate. And the capacitance is an important parameter which basically measures the ability of the device to store the charge. And very well formula, C is equal to epsilon A by D, where C is the capacitance, which we measure in farads. Epsilon is the permittivity of the dielectric medium, and capital A is the area of the plate, which is cross-sectional area here, and D is the distance between the plates, which we measure in meters. So how to increase this capacitance? For example, if we want to increase the capacity of this capacitor, then there is one way. If we have chosen the dielectric medium, then epsilon becomes constant. Now, for a given dielectric material, the capacitance can be enhanced either by increasing the surface area, that means if capital A is increased, or if somehow we could decrease the distance between the plates, that's the only way we can increase the capacitance. So capacitors are very for a very long time we know about this concept. So there is advantage of capacitor is that it quickly discharges. That means the time constant is very small. So as soon as you have powered this device, the electrical energy is stored into it. Now if you connect it into the external circuit, it will quickly deliver the energy. But there is one drawback, is that its charge storage capacity is, because For chosen epsilon, A, and D, it will have a definite capacitance beyond store the charge. So the major limitation of the capacity or of charge can store. Now we come to the concept of battery. So basically, batteries concept is also known to us chemical energy. Basically, it converts the chemical energy into electrical energy, and its principle is pretty simple, that electrical energy generation takes place by the redox reaction at the two electrodes, which we call anode and cathode. This is a classic diagram showing the working of a battery, where we have a zinc electrode, which we call anode, copper cathode, and in between boron separator is there, and zinc sulfate, that means aqueous electrolyte, and copper sulfate. Both are filled in this battery. Now, the zinc undergoes oxidation, so it loses its electrons. So because zinc loses its electrons, so it goes under oxidation, and copper sulfate, out of copper sulfate, Cu2 plus ions, they acquire these electrons, so they get reduced. So basically, there is the two half reactions, reactions taking place at each of the electrode. That's how the energy is stored chemically, and when an external circuit is we connect the load, then this stored energy is delivered to the outer circuit. Now, the battery system is considered to be a closed system. The closed system means electrodes have their active participation in terms of charge transfer, because the zinc and copper, they are taking part into the reactions. The redox reactions are happening in the presence of this zinc and copper, and they are actively participating in the mass transfer. So they basically, the mass provided by the electrodes themselves. That's why system. Now batteries, as we know, that they have a great advantage of having large storage capacity. The storage capacity of batteries is till date unbeatable, but there is a drawback also, which is slow discharge. That means it cannot deliver the power very quickly to the outer world. It cannot do it. So just a minute, please hold. So the drawback is slow discharge. Now we come to the fuel cell concept. Fuel cell, basically, in this fuel cell, fuel is the input and electricity is the output. Now the principle of fuel cell is basically electrical energy generation takes place by redox reactions at the anode and cathode. Just a minute. So electrical energy generation again takes place by the redox reactions at the anode and cathode only. But the difference from this battery is that this is an open system. That means electrodes act only as a charge transfer media. They don't actively participate. That means the active mass is provided from somewhere outside. So energy conversion efficiency is very high as compared to the batteries, and it has very low environmental impacts also. But the thing is that it acts just like a factory, and the product in the factory will be produced as far as the raw material is supplied. For example, in this hydrogen fuel cell, the hydrogen gets splitted into hydrogen ion and electron, and oxygen uh, reacts with this hydrogen and electron, and as a reduction process, water is formed. So it's majorly an energy conversion device. It's not preferably used for energy storage. Okay. And also it costs very high, and the power density is very small. Now, before we move ahead, we should look at some of the important terms which we will be going through in this talk. Though there are tens of parameters which determine the efficiency of any electrochemical storage device for energy storage, but out of them, these four, I realize that they are very essential, which will be required in our discussion. So first of all is specific energy or energy density. So it is measured in terms of watt hours per kg or watt hours per liter. You can call watt hour, that means joule also. So specific energy is nothing but amount of energy which our device can store per unit mass or per unit volume. So in terms of mass or volume, we can measure this specific energy. And specific power or power density, it's measured in watt per kg or watt per liter. And it's nothing but the amount of power our active material can deliver per unit mass or per unit volume. So there is a difference. Specific energy defines the amount of energy which is being stored into the device, and specific power is defining the rate at which this energy will be released on the, or it will be released or delivered to the outer circuit. Then cycling stability, since such kind of devices we use repetitively, we don't want it to be a one-time use and throw device. We want that a repeated number of cycles we can do with the device, but still the performance of the device should not deteriorate with the number of cycles. So cycling stability is defined as ability to complete stable and repetitive charge-discharge cycles without a deterioration in the performance of the device. Now, one more important parameter which we define as specific capacitance. Basically, again, either you measure capacitance per unit mass or per unit area or per unit volume. Depending upon that, we can define specific capacitance in terms of farad per gram, farad per centimeter square, or farad per liter. So with this, let's move. This is the Ragon plot. A Ragon plot is a plot between the specific energy and specific power. So here, all four devices, out of which supercapacitors have still not been touched. So capacitors, supercapacitors, batteries, and fuel cells have been shown on this plot, which shows that capacitors have exceedingly super specific power. That means they can deliver the power at a very high rate, but they are very low. The energy density for capacitors is very low. While in case of battery and fuel cell, the energy storage capacity is good, but power delivering efficiency is not there. That means the rate at which they can deliver the power is not suitable. So if we look at this part, the green one, supercapacitors lie somewhere between capacitors and batteries. So the gap between capacitors and batteries is bridged by supercapacitors. So what would be our next generation energy storage device? See, if we look at Dragon plot, capacitors have high power delivering efficiency, but they have low energy efficiency. They cannot store the charge very efficiently, but batteries have high energy density, but they cannot deliver the power at required rate for many of the applications. But we, the human beings, we don't, we are not ready to accept anything. Then that means we want everything to be perfect. So what is our desire to have is a device that can store and release large amount of electricity quickly with cycling stability. Large amount of electricity meets the requirement of large energy, quickly meets the requirement of rate of power delivery, and cycling stability ensures that after a number of cycles of charge and discharge, our device will be intact. Its performance will not get deteriorated. So supercapacitor is that device which is nothing but a blend of the best qualities of battery and capacitor. So that's why I have told in this dragon plot that supercapacitor somehow bridges the gap between capacitors and batteries. Now, supercapacitor, as the name suggests, it is a device with the giant capacitance. Again, capacitance is proportional to A by D. That means electrodes with high surface area and small distance between the electrodes can serve our purpose. Now, depending upon the storage mechanisms, there is a classification between the supercapacitor. One is the double layer capacitor, which we also call EDLC, electric double layer capacitor. The second one is the pseudo capacitor, and the third one is the hybrid of EDLC and pseudo capacitor, which we call hybrid capacitor. Also call it capillary. That means capacitor plus battery capillary. So let's have a look at this three devices. First of all, we look into the EDLC's mechanism. There are positive and negative electrodes. In between, there is an electrolyte field, and in electrolyte, positive and negative ions are there. In between, there is the porous separator. When this device is uncharged, then the ions are randomly distributed over the given entire volume. So there is no energy stored till now. Now, if we connect a charger, then what happens? One of the electrode gets positively charged and the other one gets negatively charged. Of course, negative ions get attracted towards the positive electrode, and these positive ions get attracted towards the negative electrode, and the separation between this positive and negative layer is of the order of 1 angstrom or so. So in nutshell, the effect of such kind of arrangement is just like two capacitors are connected parallelly, in series, and a series resistance which comes because of the electrolyte is in between. So this is the equivalent circuit showing the EDLC when it is fully charged. So we have two double layers. One double layer is this one and other one is this one. So in the EDLC, we have two capacitors in series. Now, when we connect a load with this, what happens as this negative and positive charges are accumulated on the surfaces. Now, if I connect this in outer circuit, then what happens? Because of the flow of the current in the outer circuit, it starts discharging, and while discharging, the bulb or load which is connected here will be empowered. So again, when all of the stored energy of the EDLC has been exhausted, then the device will come into the fully discharged state. And this situation, the fourth number situation, will be similar to the situation which was in the uncharged state. So this is how an EDLC works. So in case of EDLC, electrical energy is stored only by charge separation in double layer. So it is electrostatic in nature. Now, electrodes basically are taken to be carbon electrodes or activated carbon. Activated carbon is basically carbon which is heat treated under some special conditions so that pores are generated into its structure, and thereby surface area, the active surface area enhances. Nowadays, various structures based on carbons, you might be knowing about this, like carbon nanotubes, graphene, carbon dots, and porous carbons are already into the highest research. So the charge is stored electrostatically. Now, the deliverable power density is quite good. It's of the order of 10 to 15 kilowatt per kg, but energy density, because this is electrostatic in nature, so it is of the order of watt per kg only. That is not satisfactory. That means this EDLC type of supercapacitor is not suitable for any application which demands high power for long period of time, because the energy reserve is very small. Therefore, power density will be quite high, but that power will be exhausted very quickly. So the energy storage capacity of an EDLC is not very efficient. That's why we avoid using EDLCs in those applications where we require large amount of electricity to be provided for longer period of time. Now comes pseudo capacitor. Pseudo capacitor lies somewhere between EDLC and battery. Pseudo, as the name suggests, pseudo capacitor is neither pure capacitive nor bulk Faraday. It stores energy through surface controlled reversible Faraday redox reaction. As we saw in case of battery, the redox reaction or Faraday reaction takes place. So in case of pseudo capacitor also, this Faraday reversible place, and certainly it happens at the electrode-electrolyte interface, and the process, it is being limited to the region close to the electrode surface. It is a surface controlled process. So it takes place at a time scale which is comparable to EDLC. Very short time constant, they charge and discharge very quickly. So this pseudo capacitors in which the reactions are surface controlled, they all take place at the similar time scale. So the pseudo capacitive materials differ from battery materials. In a battery, the process is diffusion control, because in any kinetics, it is the slowest step which limits the rate of that reaction. So in case of batteries, it is the entire solution which takes place into the process, so it is diffusion control. But here in case of pseudo capacitors, it is only surface control. Now the preferred materials which exhibit much higher capacitance than carbon based materials are basically transition metal oxides, sulfides, and conducting polymers. Now we quickly have a look at the charge storage mechanism of pseudo capacitor. First one is the under potential deposition, in which the metal ions from the electrolyte form an adsorbed monolayer on the surface of a different metal whose redox potential is higher than the redox potential of these ions. Now basically this Pb ions, the interaction between Pb and gold is much favored in comparison to gold and gold. That's how the adsorption takes place. Now in case of this redox pseudo capacitance, charge transfer takes place near the surface of the electrode, and here in this reaction O and R denote basically the oxidized and reduced form of the redox, and ions adsorb on surface electrochemically. Since short diffusion distances are active, therefore the process also takes place in a short span of time. Now another kind of mechanism for charge storage is intercalation. Intercalation is about, like, it is the insertion of ions into the tunnels of the layers of electrode materials, and that takes place by a Faraday charge transfer. So the redox host materials of fibrous kind of nature prefer this kind of intercalation, because they have wide gaps for the ions to get inserted in channels. Now a hybrid of EDLC and pseudo capacitor is known as hybrid capacitor. So as you can see here, one side, this anode is lithium ion anode, which is a pseudocapacitive material, and on the other side, the cathode is made up of activated carbon. So basically, one of the electrode will store the energy through the EDLC process, that is double layer formation, and the electrode will store the charge via pseudocapacitance. So in order to have the advantages of EDLC and pseudocapacitors, a kind of a combination of the two have been designed, and that we call hybrid capacitor or capillary. So this hybrid capacitor also known as asymmetric capacitor, and it has high capacitance. Now we have a look at, we have a revisit to this Ragon plot. So in this plot, I have omitted the capacitor and fuel part, because the main competition nowadays for a next generation device here in terms of specific power and energy density remains between the supercapacitor and batteries. Here you see the supercapacitors can deliver high power density. So this intrinsic feature of delivering high power density is an opportunity for supercapacitor to have a competition with the batteries. But where does it lack? Its energy storage capacity is smaller than the batteries. So this low energy density is a kind of challenge. So opportunity and challenge both lie in this Ragon plot between the supercapacitor and battery. Now we all know that energy is basically defined as 1/2 CV square. So if we have energy density, then this C will be replaced by specific capacitance. So to have higher energy density, what should be the ideal conditions? That the specific capacitance C should be large. That means in a given area or given volume, my device should be able to store more and more amount of energy. That means the device should be more compact. And the second thing is that V should be more. V is nothing but operating potential window. So larger the potential window, higher will be the energy density. And you see it is V square. So small change in the potential window will have a great impact on the energy density. So having a larger potential window is always preferable to have energy densities higher. And you see, power density is defined as P is equal to V square by 4R, where V is again potential window and R is the intrinsic resistance. So again, you see that though our motto is to enhance the energy density, we are not bothered about the power density because that is sufficiently and satisfactorily high. But having a large potential window has a two-way advantage, that P is proportional to V square. So enhancing the operating potential window can further increase the power density. So that's the key point one should fetch if somebody is looking for working in the field of supercapacitors or to design the electrode or electrolyte materials which can support the supercapacitors efficiency. Then one should look at those materials which have suitable capacitance values and potential windows. Now, the one which we already discussed, there is a diagram showing what should be an approach for a high performance supercapacitor, because energy density should be high. So capacitance and voltage both should increase. In order to increase the capacitance, our active material should be porous structure with the high surface area, because porous structures provide a large surface to volume ratio. So they are preferred ones. And three-dimensional porous structures will provide us large channels for storage of the energy. So they are preferred one. And in order to enhance the voltage, basically the ion size should be small, because small sized ions can easily move in and out of the electrode materials of the pores, and the voltage window should be sufficiently high, sufficiently large, and the viscosity of the electrolyte should be as low as possible. Now, also as we saw the power density, that it inversely proportional to the series resistance. So in order to high power voltage, series should be low and resistance down by having an material of sufficiently large conductivity, sufficiently high in conductivity. Now, characteristic electron in this chemically stable. It should be corrosion resistant, because if we use active electrolytes, then the chance high. Deposit should facilitate high surface area with the active sites. Then it will be wettable. That means the better the spin electrode and more facility with the charge should be good wettable material. Then is the cycling stability. I don't need to mention this frequently. That cycling stability basically governs the life of the device. And sixth point is very specific. Like these days, smart devices and gadgets are in trend. So if we want some device to be flexible, our models should be such that they easily bended or uh, be molded in any shape. So flexibility is one added parameter. Now, why conducting polymer? Before the accidental discovery of conductivity in polyacetylene, everybody used to think that polymers are insulators. So only after the discovery of conductivity in the polymers, nowadays conductive polymers have not left any field of research where they have not penetrated. That means nowadays conducting polymers are into a high research, high research topic. So what are basic properties of conducting polymers which are favorable in our case? First one is conducting polymers can be made available at a low cost. They have intrinsic conductivity. In some of polymers, the conductivity low band. Fast charge and genetics. If you want to high charge and for consideration, if we are looking for the electrode materials, then be suitable for and dropping conductors. So depending on the requirement and type, is supercapacitors, and also species with a chemical or electrochemical, the site fit. So I've shown which is science, which is report for bird surge super polymer. So you will to an exponential growth in this researches have taken in supercapacitor field in a years. Also shows that polymers have capacity field. Also, people are how this more in some form. And the blue one shows the keyword search with electrolytes used in supercapacitors, because it's all about achieving all the parameters in sync. So the role of electrodes and electrolytes both is very important in order to achieve a highly efficient supercapacitor. And the last one, the red one, is the carbon based supercapacitor. This is highly surged because carbon based materials have long been searched, and they are very known materials for us. So the research in the field of carbon-based supercapacitors is still on its peak. Now, polymers can have their role as electrolyte. First of all, electrolytes can be aqueous. This aqueous electrolytes being dissolved in water, so they offer high ionic conductivity. And out of the available polymers, polyvinyl alcohol is the most frequently used water-soluble polymer. And it's not that it only offers good things, but there are very limitations also associated with these electrolytes. One is the narrow potential window, which is offered by these polymers, and also being aqueous in nature, the possibility of leakage is there. Then protection against the ambient conditions, and being aqueous in nature, corrosion is also highly prone. And in this, I have shown you one graph which is showing the potential window of various electrode materials in aqueous electrolyte. You see the entire range of this conducting polymers is covered within this window of 1.6 volt. Now, other than aqueous electrolytes, gel-based polymers, which we also call semi-solid electrolytes, are also being researched. And what is the gel-based polymer or quasi or semi-solid electrolyte? Basically, a polymer matrix of PVA, PMMA, PO, or a polyethylene glycol. It is basically swollen with a solution which contains conducting species, which is dissolved in the suitable solvent. So, with this, potential window can be made wider than aqueous electrolytes, and because of being gel shaped, they have tunable shapes and bendable structures. So wherever wearable electronics is concerned, this gel based polymers can be a material of choice. But again, limitation is that ionic conductivity is limited, and solubility and their contact with the electrode will be a factor which needs the serious attention. So with this, I come to the last slide of my presentation, and it's never-ending search. So there is no perfect material or method which can fulfill all the requirements which are needed for having the best device. But what the best can be done is that basically we blend different materials and different methods, so that the future lies in blending of materials and methods to yield the best results. So with this, I reached to the end of my talk. Here are some of the references. Though I have followed other references also, but somehow I could not add them into this list of references. Thank you.
Thank you very much, Dr. Pragya. Now the session is open for the question answers. If the participants have any questions, they can ask. Queries from participant sites. If anyone has any query. I can understand now the session is today's is 7th day.
Very exhaustive, actually. We get exhausted out of.
Anyway, but the presentation was so good. Very intensely review was done. And I think out of this review, for all those who are planning to work on the area of supercapacitors, or who are freshers to polymer electrolyte, you show that pseudo capacitors is a good area to work out, because less publications,
pseudo capacitors and hybrid capacitors. Hybrid capacitors, because they take the advantage of EDLC and pseudo both. So they are also, I mean, right. Hot topic nowadays.
But while coming with the hybrid and pseudo capacitors, someone may suffer with the power density. because still the your all supercapacitors are suffering with power density
Yes.
only. Otherwise, supercapacitor could be a good alternative for rechargeable batteries.
Yes, yes, yes.
But it's not
Still, sir, battery is
happening
ahead of
today.
all.
Out of all.
Yes.
Like supercapacitors are something like basically the word capacitor stands for the high density power which can be released very short interval of time and very
Yes, yes,
peak
yes.
high peak can be given. So
Yes.
taking it for a long time is still challenge with the area of supercapacitor,
Yes,
but
yes,
still I think pseudo capacitor is the good area to work out.
Yes.
Still many participants can on that work on that. So thank you very much, Dr. Pragya, for being here and giving a very valuable and wonderful talk on this. And we take this process and for the more interaction and try to make some offline conference or some workshop process in future.
Yes.
Thank you, Dr. Pragya, and thank you all the participants for joining us. And we'll join tomorrow once again with Dr. Aditya Narang is from South Korea, and he worked on he talked on the secrets of rechargeable batteries.
Okay.
So I hope all will present tomorrow, and we continue with our second last day of FDP. We'll end up on 5th of July. So till then, bye and take care. Thank you, ma'am. Thank you all.
Thank you, sir. Thank you for this opportunity.
Thank you, ma'am. Welcome.